Okay, back again here, Unit 3, Section 1, Lesson 2, Calculating Heat Change this time. Here are the textbook readings on this section and the associated questions related to this material. So you can give these guys a try, and if you have any questions, then take some of these questions to your online tutor, or you can drop me a line in the discussion postings and we can get back to you. So here we go. Here are the outcomes for this lesson. Okay, the very first thing we're looking for with heat change, remember we talked about this in the last lesson. We were talking about the idea that when we were considering a system and its surroundings, what we have to keep in mind here is that for a specified universe, the energy transfer is going to happen between the system and the surrounding. And we try to ignore, I guess, or not necessarily ignore, but we try to eliminate other factors that would influence our system and our surroundings. So for instance, if we created or carried out an experiment where we tried to see how much energy it took to melt ice in a styrofoam cup, we would think that the styrofoam cup would be insulating the outside environment. So what we would be mainly concerned with would be our system, which is the melting of the ice, and the surroundings, which is inside the styrofoam cup, which would be the water that would be in there. So in that context, then we could say that the universe is inside our cup, and any energy that's being transferred is being transferred from the water to the ice. There's none being lost to the outside environment. There's no energy being created. There's nothing being destroyed. Energy is simply being transferred from the system to the surrounding. Okay, so in this sense, we're saying that it's the system and the surroundings that involve the energy transfer. So in this case, we're saying that the delta sign here, this little triangle sign, refers to the change in energy. And up here, we're saying that the change in energy of the universe is 0, which means there is no change. There's no loss of energy. There's no gain of energy. All that happens is energy is being transferred from one to another, and there's no loss of energy during that transfer process. So we're looking at this and we're saying, okay, if the first law of thermodynamics is telling us that there's no loss of energy, then we can simply substitute that 0 in right here, and therefore the equation gets manipulated to say that the energy change of the system is equal to the negative energy change of the surroundings. In other words, the energy lost by the system was gained by the surroundings, or vice versa. The energy gained by the system was lost by the surroundings. So if ice is our system inside that styrofoam cup and water is our surroundings, the water would have to gain energy to melt. Well, where is it getting that energy from? It's getting it from the energy lost by the water. Okay. So energy is transferred from the systems to the surrounding. Now, for all intents and purposes, E refers to the total internal energy. So this would refer to all forms of energy, potential energy, kinetic energy. If we're talking about firing a rifle or a shotgun or something like that, or, we have heat energy from that. We have sound energy because it makes a great big bang. We also have light energy coming from the flash of light that would come from the muzzle of the gun. And we would also, of course, have the kinetic energy of the bullet as it moves. These would all be the forms of energy we're talking about in that sense. So for us, we're going to try and keep it simple. We're going to simplify it here and say, well, we're not interested in the kinetics of the bullet, and we're not really interested in the amount of energy from the sound or the flash of the bullet. What we're interested in is the change of heat energy. So we're going to try and limit our study here in chemistry. We're going to be focusing on the heat energy. And we have to realize that, of course, yes, when something like gunpowder goes off, yeah, there's a lot of heat energy that's exchanged, but don't forget now there's also the expansion of the gas, which is energy, the kinetic energy. It's going to be the heat and the light and the sound and all that stuff all combined. So we're going to simplify this a little bit and say, okay, we're simply going to focus on the heat energy that's going to be transferred from one body to another. In our case, the heat energy that's going to be transferred from the system to the surroundings. And when we refer to heat energy, capital E, remember, refers to the total energy. All forms of energy that something would have, kinetic, heat, light, sound, all that. We're going to focus on Q, which means we're simply going to focus on the heat energy that's going to be exchanged from the system to the surrounding. So in this case we say Q, heat of the system, is equal to minus Q of the surrounding. So any heat gained by the system is going to be equal to the heat lost by the surroundings, because of course no extra energy is coming into this universe and no energy is being lost to the universe. All the energy is getting transferred from the system to the surroundings, or vice versa. Our unit for calculating this, or our unit of measure for measurements of heat energy, is going to be the International System Unit called the joule, capital J, because it's named after a fellow, James Prescott Joule, so it's a capital J. A simple idea here, I guess, or the way we look at this is we can say 1 joule is not a lot of energy, but when we have 1,000 joules, that refers to a kilojoule. So kilo represents 10 to the 3 or 1,000. All right, so 1 kilojoule is equal to 1,000 joules. And if we look at a larger amount of energy, we can look at 1 million joules. That would be represented as a megajoule. Now that's a significant amount of energy. And mega, of course, would represent these 6 zeros, so 10 to the power 6. So 1 megajoule would be 1 times 10 to the power 6 joules, and 1 kilojoule would be 1 times 10 to the power 6 joules. All right, so we could look at this and say 1.0 times 10 to the 3 joules equals 1 kilojoule. Okay, another way we can look at this one down here is we can say 1.0 times 10 to the power 6 joules is equal to 1 megajoule. So these would be the different units we would use to describe the amount of heat energy that we're talking about. So if we're only talking about a small amount of energy, we would refer to it as a joule of energy. If we're looking at larger amounts of energy, like for instance the melting of ice takes 6 kilojoules of energy per 1 mole of water. All right, so more on that later. Sometimes we refer to heat energy in the form of a calorie. Lots of times when we talk about food energy and stuff like that, we refer to it as calories. Now calories is an older way. It's more of an imperial method of measuring heat energy, just like when we measure like amount of gasoline. In the old days we used to measure it as gallons. So you would go to the gas station, you get 5 gallons of gas for your skidoo. We don't measure things in gallons anymore. That's the imperial method. What we use now is the metric system, which would mean we'd go to the store and we'd buy 22 liters of gasoline, which is equivalent to 5 gallons. For us, the imperial method would have been calorie, and the metric unit, the SI unit, would be the joule. Okay. Now for us, sometimes we see energies being portrayed in calories. So what we would have to do is make sure we would know how to convert a calorie to joules. And what a calorie is, by definition, is the energy it takes to heat 1 gram of water by 1 degree Celsius. And the amount of heat it would take to do that is considered to be 1 calorie, which equals 4.184 joules, or 1 calorie equals 4.184 joules. And this is going to be easy for us to remember because this is the heat capacity. More on that now in a few minutes. This will be the heat capacity of water. All right, so that's how they derived that value. So 2 different ways of measuring energy. We're going to keep it to the joule because, of course, we're metric. Okay, what are some of the factors then that we would have to consider if we were going to calculate the amount of heat energy in something? Well, the very first thing we'd have to consider is, well, how much of the material is there? The more material we have, we looked at that last day, a transport truck requires a lot more energy to get it going to 100 than, say, a small car, because the transport truck is more massive. It requires more energy. So the more mass that's involved, the more heat it can obviously hold. A big rock stays warmer longer than a little tiny pebble because the big rock is more massive. The other thing we want to look at is, what is the material made out of? you know, air can hold a certain amount of heat energy. Water can hold a lot more. So in, say, summertime, nighttime, when the air cools off, it might drop down to, say, 8 or 10 degrees nighttime. The water is still very nice and warm because the water is holding on to its heat longer. So by the mere nature of the material, the water has a much higher heat holding capacity than air. That's why water cools off. It takes a lot longer for water to cool off. Air cools off real quickly. So we would refer to that as the heat holding ability. And that would be what we refer to as the heat capacity. How much heat can it hold? What's its capacity for heat? And in this case, we measure this by saying it's the amount of heat that an object would undergo a 1 degree change in temperature. Now you notice here we're saying it's simply the amount of heat needed to cause it a 1 degree change in temperature. There's no mass involved here. So this would refer to an object, like say, you know, how much energy does it take to heat up a frying pan? A frying pan has the pan plus the handle and maybe a top cover on it and something like that. So we would see how much energy it would take to warm that entire object 1 degree Celsius. You know, like an engine of a car has many different parts made of many different types of metal. There's rubber, there's plastic there. How much energy does it take to heat that car engine 1 degree, taking into account that it's got so many different parts made of so many different types of material? All right, and that's heat capacity. Now we want to be more specific than that. We want to figure out what's the heat capacity of a pure object. I mean, it's no good. It's very difficult for us to use a frying pan if we're going to do some experiments here. We want to use a pure substance, like a pan that's entirely iron, or a pan that's entirely copper or entirely aluminum. We want to get off that plastic handle or that wooden handle and just use an entire object that's the same material. So we want to be more specific, and therefore we would have to do something called a specific heat capacity. And this is going to be the energy needed to change the temperature of 1 gram of a pure substance by 1 degree Celsius. So there's no confusion, there's nothing else involved, there's only one type of metal or there's only one type of liquid, and it's a pure substance. We would take 1 gram of it and see how much energy it takes to heat it by 1 degree Celsius. So for instance, the specific heat capacity of water, pure water, is 4.184 joules for 1 gram to heat it 1 degree Celsius. All right, the heat capacity of ethanol would be less than half. For pure ethanol, 1 gram of it by 1 degree, it would absorb 2.01 joules of energy. So that's very specific. Therefore, we call it a specific heat capacity. You notice the difference here in the units. Heat capacity is simply joules per degree Celsius. This guy over here is joules per gram degree Celsius because it's specific for a specific quantity of the pure material. Okay, there's a whole bunch of tables here in your textbook. Page 632 of your textbook, there's a table of all different heat capacities. On your public exam, they would generally give you the heat capacities that they would want you to use within the questions. All right, there's a couple there that you would have to remember, but they would be found on your public exam data table, all right, where they would give you the specific heat capacity of pure water, gas, pure water, vapor, and pure water solid, all right, ice. So they would be on your data table. Okay, so heat capacity is referring to heat holding ability. If you have a high heat capacity, that means you can hold more heat. So in the example we gave up here, water has a heat holding capacity of 4.18 joules per gram. Ethanol only has a heat capacity of 2.01 joules per gram. So water is capable of holding twice as much energy as the same amount of ethanol. So its heat capacity is double. All right, number 3 here, of course, the temperature is going to be so vitally important as well because the amount of heat, not only does heat depend on the mass or the amount of material you have, it's also going to depend on how excited are we going to make it. You know, what's the temperature change going to be? Are we going to go from 20 to 80, 20 to 60? Are we going to go from minus 20 to plus 20? You know, what's that temperature change? Because we know that mass, energy is 1/2 mass times velocity squared for the kinetic energy, so it's dependent on mass as well as the speed of the particles, which we found out in the last lesson was the temperature. So the amount of energy something has depends on how much we have, what the substance is, and what is its temperature change. So just a couple of little demonstrations here to show you what we're talking about. In this case, we're doing an experiment where we have exactly the same type of substance, pure water in both beakers. They're at the same initial temperature, and the only difference, of course, we're adding the same amount of ice. The only difference is this guy has a different amount of water. This one has 60 grams of water. This guy has twice as much, 120 grams of water. What we do is we drop in equal amounts of ice and we watch the substance cool off. And as we watch it cool, we notice that the first beaker cools off to a greater degree than the second beaker. This is the initial temperature, that's the final temperature. And this should be making sense because, after all, the temperature change is going to be larger here because we have half as much mass. It's going to cool off much more quickly because we have less of it to cool off. So beaker 2 cools off less than beaker 1 since beaker 2 has more water to cool. This one's going to have twice as much energy, so therefore it's going to take a lot longer for it to cool off. So therefore more mass is able to hold on to more heat. There's more molecules that are vibrating. Okay, here's another demonstration. In this case we have canola oil and water, equal amounts, so the exact same mass, so the same amount of matter. The initial temperature is the same. Once again, we're going to throw in the same amount of ice in each beaker. What we find is that the water cools off to a large degree. Water, in this case, is going to lose 30 degrees. All right, so the temperature change here is almost 30 degrees, whereas the temperature change here is only 18. So what we're saying then is water cools off a lot more quickly. So water is less able to hold on to its energy than the canola oil. The canola oil hangs on to its energy much more efficiently, I guess, or it has a much higher heat holding capacity. So in this case, because water cools off more quickly, it has a smaller heat capacity than the water, or vice versa, oil has a much higher heat capacity than water. The oil is going to stay hot longer because it has a higher heat holding capacity. Okay, here's an example then that's comparing different types of specific heat capacities again. In this case we have a 1 gram sample of copper, iron, aluminum, and 1 gram of water. What we want to do is we're taking equal amounts, so equal amounts of matter, and we want to see which one can absorb the most energy per gram. All right, so what we're going to do here is we're going to look at this and say, all right, the very first thing we have to do is acknowledge that these guys are all different. So therefore, they should have different heat capacities. And I looked up the tables and I found the heat capacities of iron, copper, iron, aluminum, and water. Okay, now what we're looking at is we're saying, okay, if we have a 1 gram sample, how much energy is that 1 gram sample capable of absorbing? So I'm going to make an example here and say, let's put 10 joules into each one of these 1 gram samples. And we're going to figure out what the temperature change is going to be. So in each calculation, I'm doing this real quick here because what we're saying, it's a 1 gram sample and we're going to divide it by its heat capacity. And what we're going to find is that for the copper, absorbing 10 joules of energy, it's going to change its temperature by 26 degrees. That's a significant temperature change. If we look at iron, which has a higher heat capacity, the same amount of iron absorbing the same amount of energy is only going to change its temperature by 22 degrees. So it's going to stay colder. It's going to be cooler. The aluminum, which has an even higher heat capacity for absorbing 10 joules of energy, is only going to change its temperature by 11 degrees. That's not going to get very hot at all. All right? So the temperature change here is, you know, less than twice of what copper is changing. And in the case of water, where the heat capacity now is 4 times that of aluminum, what we notice is that its temperature change is very tiny because it has an ability to hold on to a lot more energy. So what we see is with the higher heat capacity, we see smaller changes in temperature because the higher the heat capacity, the more energy it can absorb without showing a change in temperature. Now, a couple practical questions that go along with this. We would say, all right, well, based on this idea, which substance would you like to make a snowmobile engine out of? An air-cooled snowmobile engine. And the answer would definitely be, I want a snowmobile engine that's going to operate at as much energy as it possibly can, but not change its temperature. And what we're looking at here is we're saying, well, aluminum is our example here, because aluminum has the highest heat capacity of the three metals. It's going to be able to absorb the most heat energy and show the smallest change in temperature. And in that case, from the kinetic molecular theory, remember, the higher the temperature, the more expansion we get. So if we operate at a smaller temperature, that means we're going to get less expansion of the metal, which means now the snowmobile engine is going to last a lot longer, because the particles, the parts of the engine are not going to expand, because it's going to operate at a colder temperature. All right, so if we had an engine made of copper, the copper engine would be, one second, oh. Okay, back again. I kind of lost my breath there. My voice has changed now, so we'll just bear with it here. Okay, so what we're saying then is that the aluminum is going to change its temperature very small, so therefore we get less expansion because the engine is operating at a cooler temperature. So it follows then that what would be an application of copper then? Well, because copper absorbs less heat, that means more of the heat would be transferred through the copper, which means it would make it good for making pots and pans and things like that. So you've heard the expression a copper kettle. A copper kettle is good for boiling water because the copper heats up really, really quickly, and all that energy then can get transferred to the water and would boil the water more quickly. Pots made out of aluminum are not very good, because the very first thing you have to do is you have to try and heat up all that aluminum, which absorbs an enormous amount of energy, which means that energy is not being transferred to the water. So an aluminum pot is far from ideal. Copper would be better as a pot. So the next question would come up, well, what would be the advantage of having a liquid-cooled engine? And the advantage, of course, is that the water has almost 4 times as much heat capacity or heat holding ability as the aluminum. So if this guy had a high heat capacity compared to the metals, and it only changes temperature very slightly, water would only have a very minor change in temperature, which means now the engine would show very little expansion. The metal parts would not be heating up that much, so the metal parts would not expand and therefore cause wear and whatnot in the engine. So the water has a very high heat capacity. It's going to absorb more than 4 times the energy, and therefore the liquid-cooled engine now can operate at much higher energies, higher horsepowers, at cooler temperatures. And that's a good thing, because at cold temperatures the engine doesn't expand and therefore it won't wear out. Okay? So the idea I'm getting from this is my little footnote. Very important idea here from this is that the higher the heat capacity, the smaller the temperature change. Right? Highest heat capacity, smallest temperature change. Smallest heat capacity, largest temperature change. So the higher the heat capacity, the smaller the temperature change. The smaller the heat capacity, the greater the temperature change. So we could do something like this and say that heat capacity, which is going to take the symbol C, and temperature are inversely proportional. Okay, these guys are inversely proportional, which means as C goes up, T is going to go down. All right, and that's what we mean by an inverse proportion. And the opposite is true as well. If C goes down, T is going to go up. Seen multiple choice on the public exam based on these same ideas, right? They gave you 4 heat capacities. Which one shows the largest heat change? The one with the smallest heat capacity shows the largest temperature change, and then the other way would be, of course, which one would show the smallest heat change, and that would be the one with the largest heat capacity. So there we go. All right, so let's put it all together now and say we know that heat energy depends on the mass, the specific heat capacity. There's the mass, there's the specific heat capacity, and this symbol here means change in temperature. So, Q is the heat measured in joules, M is the mass measured in grams. C is the specific heat capacity. Take note here, joules per gram degree Celsius. And delta T, or the change in temperature, is going to be TF minus TI. In other words, the final temperature minus the initial temperature. Once again, the heat capacities are listed. There's another table on page 847. These values are listed on your public exam data sheets. All right, so don't confuse here now. Just because they give you water in a question, the state of water is very important, because liquid water has a much higher heat capacity than solid ice versus gaseous water. So keep that in mind. If they give you water in a question, you have to make sure and say, okay, well, what's the state of water? One way you can do this is say, well, what temperature are we at? If we're at -10, then we know water is going to be frozen. If we're at 25, we know water is going to be a liquid. If we're at 150, we know we're dealing with gases. All right, so keep that in mind, that they are different. Okay, sign convention. Every time we refer to an energy change, remember in the last lesson we talked about the systems and the surroundings, we always express the energy with respect to the system. So if I'm going to state an energy change, I have to say it's with respect to the system. Did the system gain energy, or did the system lose energy? And in this case we're saying if Q is positive, that means the system has gained energy. That would be an endothermic change. It's gained energy. And that would give us a positive value for Q. So in this case we're saying, okay, if Q is positive 40 kilojoules, what that means to us is that it's 40 kilojoules of energy gained by the system. Okay? The other convention here is that if we have a negative value, then that's referring to energy lost by the system. So negative energy has been lost. That's going to be an exothermic change. Look at the mistake I got there. I know you guys all picked up on that, so let me fix that for you. This is going to be exo. Okay, there we go. So exothermic. And what we're saying here is it's a negative 40 kilojoules. So this implied, it means that 40 kilojoules of energy was lost by the system. Okay, so always with respect to the system. Another thing we need to look at here is the density of water. Sometimes they give us questions where they give us the volume of water. And our calculations, Q equals mc delta T, refers to the mass of the water. So what we want to do is assume that at 25 degrees Celsius, 1 gram of water has a mass, 1 milliliter of water has a mass of 1 gram. So if they gave us a question and said we had 150 milliliters of water, the mass of that water would simply be 150 grams. Because 1 milliliter weighs 1 gram, so 150 milliliters is going to weigh 150 grams. Okay? And there's our calculation for that right there. So density is mass over volume. Okay, let's do a couple sample problems. In this case, we're saying a student has 225 mils of pure hot water in a lab procedure. Calculate the heat change involved in raising the temperature of the 225 mil sample from 20 to 100. Now the very first thing I like to do with these problems is I like to write out what I'm given and what I need to find. All right. Now in this case, I'm given the volume of water, and right away I'm saying since the density of water is 1 gram per mil, then that's going to refer to 225 grams of water. I've got my initial temperature given. That's where I started, 20 degrees Celsius. I've got my final temperature. That's where I ended, 100 degrees Celsius. So therefore I can calculate my change in temperature. It's TF minus TI. So 100 minus 20, it ends up being a positive 20, or 80 degree gain in temperature. Okay, there's one other piece of important information that I haven't listed, and that's the specific heat capacity of water. Even though they did not give it to us in the question, we have to be thinking now and say, okay, what substance are we heating? Well, it's pure water. So you go to the table and you get the heat capacity, or sorry, the specific heat capacity for pure water. That's 4.184 joules per gram degree Celsius. So they don't give you that, it's in the tables. What we have to do now is say, all right, we can calculate Q here. Q equals mc delta T. We know everything we need to know now. So we put our values in. Very important that you write the units here. 225 grams times 4.184 joules per gram degree Celsius times TF minus TI. And we're looking at this and we're saying, all right, do the calculation. I just did my delta T there, and now I figure this out. Now watch what's going on here. Grams is on top and bottom, they cross out. Degrees Celsius is on top and bottom, they cross out. My final answer is 75,312 joules. That's a lot of energy. If I look at this question, that's way too many significant digits. My question, this guy has 3, 3, 3, 4 significant digits. This value has 4 significant digits. I'm multiplying here. When I subtract, this should have 1 decimal place, but I'm multiplying here by 3 digits. So my final answer should only have 3 digits of significance. So what I'm going to do is I can either express it in scientific notation, or I can simply express it in kilojoules. And scientific notation, I'm going to move my decimal place from here, 1, 2, 3, 4 times. So it's going to be 7.3 times 10 to the 4 joules, or in order to convert it to kilojoules, I simply divide it by 1,000, which works out to be 75.3 kilojoules. I like doing it this way, but you might see it this way too. Now, because this is positive, and that comes from this right here, the temperature went up. It was a gain in temperature, which means it was a gain in heat energy. So the value plus is very important to state the plus or negative here. In this case, it's a positive value. So that means the water, which is our system, gained 75.3 kilojoules of energy. There we go. Here's another example where we compare two types of metals. We're going to compare iron to aluminum. We've got equal masses of these substances, 175 grams. They're warmed in a hot water bath to 99.7. So what that means is they were put in boiling water, and they sat in boiling water for a long period of time. So we know that the iron and the aluminum will be the same temperature as the boiling water, right? They're at thermal equilibrium. What we're going to do is we're going to take these hot pieces of iron and aluminum, and we're going to drop them in 2 different styrofoam cups that have some water in it, and the waters, they're going to be cooled down to 21.5 degrees Celsius. So we want to be able to measure the heat change of these 2 substances. So let's work through this, and we say the mass is 175 grams. We know TI and TF. And because we know this is iron, we know its heat capacity. We can look it up in the book, and we get that value. So we can easily calculate the energy change of the iron, Q equals mc delta T. So we put our values in here, and lo and behold, the grams cross out, the degrees Celsius cross out, and what we find is that the iron, because this is a loss of temperature here, we're starting at 99 and we're cooling down to 21.5. The difference here is a negative 78.2 for the delta T. So we're cooling off, which means that piece of iron is losing energy, and that's reflected in the question. So a negative 6.08 kilojoules, therefore the iron lost 6.8 kilojoules of energy, 6.08. We do the same thing for the aluminum. Same mass, initial and final temperatures are the same. The aluminum is the same. Sorry, the aluminum has a heat capacity much larger than the iron. We found that out already. So we're going to predict that because this guy, everything else is held in control, they're all constant, same amount, same temperature changes. This guy has a larger heat capacity, which means it should show a smaller change in energy. And what we're seeing here is that Q equals mc delta T, once again, okay, a larger change. Actually, it's holding more energy for the same change. So the change here is still going to be minus 78.2. So in undergoing the exact same change in energy, this guy is going to release a lot more energy because it has a much higher heat capacity. And here we go. We plug it in. We get a negative 12,316, which works out to be, divide by 1,000, negative 12.3 kilojoules. So what we're seeing here is that the aluminum loses 12.3 kilojoules of energy as it's cooled. And the significance of this, aluminum was holding twice as much energy because its heat capacity was twice as big. So cooling it over the same temperature range means aluminum is going to release a lot more energy because it has a higher heat capacity. And this goes right back to that question of heat capacity. The higher the heat capacity, the more heat it's able to hold. Okay, heat capacity values can be determined for specific devices or pieces of equipment. So like if we wanted to figure out the amount of energy gained by, say, a frying pan, we would want to look at this and say, okay, let's look at the frying pan, and they give us the heat capacity. Now you notice what's missing here? We never said specific heat capacity. So in this case, it's the object that we have the heat capacity of, knowing full well that this frying pan is composed of probably a plastic handle, a cover, a lid with a plastic cover or lid on it, and handles maybe. All of these objects that are attached to the frying pan are going to absorb energy. So rather than specify each individual component, we simply say, let's take the object, and this object now has a heat capacity of 1.2 kilojoules per degree Celsius. So there's no mass in this value. And because there's no mass in this value, we simply say that the change in heat is not going to be based on mass anymore. It's going to be based on the object itself. So Q is only going to equal C delta T. And you notice that the C is a large C, so it's not dependent on mass. So let's have a look at this. So the frying pan with heat capacity of 1.2 kilojoules degrees Celsius is heated from 22 to 198. Calculate the heat change. Okay, we write down what we're given and what we need to find. So in this case, we're given the heat capacity, capital C, of the pan. You notice here I'm specifying what the heat capacity is. It's 1.2 kilojoules degrees Celsius. Ti and Tf are given. No mass is given. So what we simply do is we say, okay, if no mass is given, then we do not include mass in our equation because the specific heat capacity does not have mass in it. So Q equals C, Q pan equals C pan delta T. So we put our numbers in, and you notice here, again, there's no mass in this unit, so we do not have to cross out grams or anything like that, so we do not include it. So 1.2 kilojoules degrees Celsius times 198 minus 22, and in this case, what do we get? All right, so the degrees Celsius are going to cross out, and I'm left with 211.2 kilojoules. And in this case, we should really have two significant digits, but I've stated 3 there. I'm going to change this and say that that's 22.0. How's that? Nah. What I'll do is I'll say, okay, it should be really 2 significant digits. So I would really express this as 210 kilojoules because it should only be 2 significant digits. And the 2-1 is significant, the 0 is not because there's no decimal place in this number. If there was a decimal there, then the 0 would become significant. But because there's no decimal place, only the 2 digits would be, the 2 and the 1 are significant. So 210 kilojoules. And this is a positive value, so that means the energy is being absorbed. Positive, positive. Okay. Here's another one. This one says calculate the specific heat capacity this time of an unknown alloy. So we got some type of metal that we'll never find on our table. So we don't know what the specific heat capacity is. We don't even know what the metal is made of. All we know is that if we take a 15-gram sample and we heat it up and it absorbs 393 joules when we heat it from 0 to 37.6, we want to figure out the specific heat capacity. So again, we write down what we're given and what we need to find. We need to find the specific heat capacity of the alloy. We're given its mass, the heat energy that it absorbs, and the change in temperature. So here we go. Q equals mc delta T. What we need to do here now is rearrange to solve for C. So in order to solve for C, I'm going to divide both sides by m delta T. That way, on this side, the masses cross out, the delta T's cross out. So my formula for calculating C is going to be C equals Q over MT. All right. I put my values in, and in this case, we have to say that it's a positive term for Q here because it's telling me that it's warming up. It's going from 0 to 37 degrees, so it's getting heated up. So it's going to be a gain of energy. so a positive 393. When we do our calculation, okay, the specific heat capacity works out to be 0.6787 joules per gram degree Celsius. There we go, 3 significant digits. Now, the specific heat capacity should always be positive because everything that's made of matter absorbs energy. So everything absorbs a certain amount of energy. Some things gain a lot of energy, would have a high heat capacity. Some things only gain a little bit of energy, they have a low specific heat capacity. But in any case, all objects, all matter would absorb a certain amount of energy, so these values are always going to be positive. If you end up getting a negative value here, you better check what you just did with your temperature here. Make sure you got TF minus TI. And make sure you read the question again to see, are we gaining energy or are we releasing energy? Because if this sign is negative here, then this should end up being a negative too, so the negatives would cross out. So we should always get a positive value for specific heat capacity. Okay? On another note here, we could now identify what type of metal this is, because if they told us we didn't know what the metal was, but yet we calculate the specific heat capacity, if this turned out to be the specific heat capacity of gold or iron or copper, then we could probably identify what type of metal we were dealing with by looking at its specific heat capacity. Okay, here's a few more sample problems. Again, you can check these out with some of your online tutor, or you can fire me off a discussion email on this if you want to show me your workings or something if you can't get these guys to work out. But in any case, that's it for these calculations. And if you want some more information, of course, check the examples in your textbook. And here are some other textbook problems. The answers to these are in the back of your book and at the end of the chapter. Give them a try, have a look at them, and again, make use of your online tutors. They're there to help, and they're free. All right, see ya.